Okay, welcome to the fourth lecture on the course called Foundation Models in Generative AI. Today we will do a very brief mentioning of data. Data is one of the key components in this new type of AI and really deserves its own course, but we're going to talk a little bit about it. And then we're going to cover Stable Diffusion, which is a text-to-image generation AI, generative AI. Okay, so what do we have left on this course? So next week we are going to have a lecture on emerging foundation models and their applications. So this is foundation models in the wild, in the market and in commercial settings, especially. We'll have two guest speakers as well. So Manolis will talk about AI in genomics and applied biology, and Artem will talk about autonomous agents. And then the last lecture will be on AI ethics and regulation, and then we'll have a panel at the end of it and discuss the ethical aspects of AI. Okay, so to summarize a little bit, right, the first lecture was an introduction, a very quick, intuitive answer to what is foundation models and generative AI. We went on a little bit of a philosophical digression and the history of AI. The second lecture went through all the different algorithms from a high-level perspective, and then we went into depth. The last lecture on ChatGPT. Right, so what do we do what's the key behind foundation models? It's be able to learn from observations. You don't need human beings in the loop. You can scale up as much as you want. And that you get from this is a very kind of contextual relational understanding of meaning. That meaning is defined by the company it keeps. It's self-referential. Right, so a dog is something that's walked by an owner with a leash. It's something that has an antagonistic relationship with cats. It's something that chases frisbees when those are thrown. This is how we understand what a dog is, right? Not actually your parent labeling it or really you optimizing certain goals like reinforcement learning. It's you observing dogs in different contexts and correlating dogs with other concepts. That's how you understand what a dog is. That's that's the main trick. Again, something that I think is true when it comes to AI is that there's a most understanding is intuitive and it relies on all these different relational edges. So you don't never really fully understand something. You can always become better, and it's a lot about just familiarizing yourself. So if you don't understand everything in lecture, that's fine. Just try to get some intuition and familiarize yourself with it, and then kind of keep going. Okay, so data. Why is it so important? Well, I think a kind of complementary perspective on all the breakthroughs in AI that we've been seeing is thinking about in terms of data, and actually how the new AI just looks at data, the old type of data, but looks at data in a new type of way. So it becomes more powerful and can use more of it. And that's basically a very big part of what's happening right now, and the data is really, really key. And in some ways, I think data is if you want to apply AI in actual settings that you might care about, looking at the data, understanding the data is going to be key for you. So that's a very interdependent concept. Like AI and data goes hand to hand. It's very, very hard to develop better models if you don't understand the data and vice versa. So if you start applying AI to your own settings, understanding how the data, what data you have, and also how AI leverages data and what kind of data it wants, is going to be very, very important for you. And if we take this picture we had before about kind of look at this new AI development as some kind of iceberg, right? The tip of the iceberg are ChatGPT and Stable Diffusion, for example, right? Hype stuff that people are talking about, and then of course below that, it's about understanding self-supervised learning, the training methodology to get these AIs, right, on foundation models and generative AI, and then a really big, a significant chunk below that people don't talk about as much is the data, right? That's what feeds this whole revolution. Right, and I think so. Let's look at OpenAI, for example, they built ChatGPT, right? Maybe it's like 10 engineers working for a year or 6 months actually developing the ChatGPT version that we're using right now, right? That's not a lot. I mean, that's why you have a lot of startups now that try to replicate ChatGPT, just with a lot of money and compute to train on data with a small team, and they can reproduce it. So that's like in itself, I mean, it's of course impressive, but it kind of pales in comparison to how the internet was created, right? So that they're able to leverage all of the internet, download it, and train on it. But the internet was, we spent 20 years, billions of people putting a lot of data online. That's a huge effort that you cannot replicate, right? Nobody can replicate that process of creating the internet from scratch. No company can. It would be too expensive. And so somehow the internet makes all this available, and is basically the greatest data collection effort in human history. And that's, I think, is even more vital for ChatGPT than any of the technology, right? So data is really, really key. And again, I mean, if I had to choose between, and for you as well, if you had to choose between having ChatGPT or having the internet, you would rather have the data and the internet, because you can retrain ChatGPT and you can create better versions. So the data is really key, and having access to it. And as well, it's also going to be problematic now with copyright, etc., where people want to say, like, well, Stack Overflow. But we have this data, and now you're kind of out-competing us by using our data. And people are going to value data more and more now as well. And it becomes very interesting how it's going to affect the development of AI. Because the internet has been so easy to use, and people haven't really cared. And again, when you work for a company, whatever you do, and you have your own problems, start looking at the data. The data has all the secrets, so it's very, very important to think about and not overlook. All right, so the small piece of philosophizing in this class will be about data. So I mean, equally that for ChatGPT, the interesting thing is not the technology, right? It's not the brain of ChatGPT, but it's the internet. Maybe it's a similar perspective of us human beings. Like, maybe we're not that impressive as intelligence, but actually the data that we've created and the whole biosphere has created, that's what really matters. So maybe we're just more data creators for the gene, for example. If you know about this theory about the selfish gene trying to reproduce itself, like maybe we're just collecting data for another purpose, basically. So, right, let's say that an alien came to Earth and discovered Earth, and we'd be like, oh, they probably want to kidnap us and look at our brains and dissect us to understand us. Maybe they'd be like, well, no, we don't care about you guys. We want your data. We just want like all the history of the Earth and what's going on here. Collect that, and then they can derive their own human beings, even improved versions. So maybe it's like the data somehow is really, really key, and we try to focus. I mean, sometimes we focus on the AI itself, but the data behind these creations are extremely important. All right. Okay, so conditional image generation, text-to-image generation, that's what we're going to talk about today. So two of the first most popular models here was called Dall-E and Stable-Diffusion. So this is a year ago, and you can see the two different versions compared. On the left-hand side, you have Dall-E, and on the right-hand side, you have Stable-Diffusion. And this says a high-tech solar punk utopia in the Amazon rainforest. So it does a good job, looks realistic, and it adheres to the prompt, and it has some kind of imagination as well to be able to create this. And we can just check quickly how it's progressed. So this is GPT-4 now, asking the same thing. I would say it looks even better. So that's good. There's been some progress. Of course, almost all of the images that's in these lecture slides are from these text-to-image models. And this is how I created this strange image. So prompting can be quite hard. I think prompting has become easier and easier. But you can also sell prompts online to get, for people who can get exactly the image that they want. So that's interesting. I think that people were very hyped about prompt engineering in the beginning, but now it seems to be a little bit less hype. And as the model becomes better, it's also easier to create the prompts and the images that you want. And again, this is also a year ago where Facebook, I think, Google released this Imagen. So they went from text to videos, which was something that we've seen improved substantially, and hopefully this year we'll get something that works extremely well, so we can start creating videos from scratch. Of course, the underlying approach and technology is very, very similar, but you have to scale up now and think about frames, right, which is just a collection of images. Okay, so to be able to successfully create images and have a text-to-image conditional generation, there's a few things we want to accomplish. So we want to have a high real image quality. We want our images to look real, realistic, right? That's important. We also want a high correspondence between language and the image that's being created. So if we write something, we want something that looks like what we're writing about, right? We don't want to write something and then get something completely different. There's going to be a strong correspondence. And also we want to somehow capture a variety of images around a concept. So let's say we want to generate a dog. We want to be able to generate all possible dogs somehow. That's going to show that the AI understands what a dog is more, what a dog is in a more nuanced sense, because it can create all the different versions. And it's going to be useful as well because you want to sample and it shows some kind of performance criteria. And we want it to be fast to train and to use. So how do we accomplish this? Well, we're going to use engineering and smart tricks to accomplish everything besides high language and image correspondence, which we'll have to rely again on data. So it's going to be, you can say it's labeled data, so it's correspondence between images and text. You can get it up from you can get that from different scripts and scraping online, but you need that correspondences to get a really good performance. You can reduce the need for data, but you need to have that data in how you build these models so far. Okay, so let's just talk about how we can go about this. How can we learn to generate images? And maybe we can first talk about drawing faces as a starting point. So let's say we want to learn to draw faces. We want to train our AI model to learn to draw faces. And we arrive at something that's able to generate the same face over and over again. Right? Do we trust this model somehow does a good job and it's able to understand what entails a face or what's included in a face? Probably not, because it collapsed a single instance, maybe just memorizing something. So we want to have some variety. But also for it to be more useful, we want to be able to say, like, generate 10 faces I can use in my slides, right? And you want different faces, you don't want the same face. It's less, the utility is decreased. So you want to be able to generate different things. So the first thing you will notice when you think about it is that, okay, well, these deep learning models are still deterministic functions. So if you give it the same input, you get the same output. So there's no randomness here for the new network to leverage to create different samples or instances. If you give it the same input, it's going to produce the same output. And randomness is very, very hard for a new network to kind of create by itself. So you need to feed that randomness as an input to it, like it's as part of its environment, let's say. And maybe it's the same for ourselves as well, that if you would be able to very, very carefully recreate exactly the same environment, you would also act in very similar ways if you find yourself in exactly the same environment. And maybe that when we find ourselves in new environments, actually, that's conducive to us being creative. So maybe we can learn something from this as well. But it's very important for networks, at least, that we give them some randomness that they can leverage to explore and generate different versions. Okay, so we're gonna, as part of the input to the new network, we're gonna feed some randomness, right? So it's gonna, every time it's run, it has some different type of input. So you can leverage that to say, like, hey, I'm gonna now create a face that looks like this, or like a face looks like that. It can leverage this randomness to create a distribution of faces. So now, each time when it gets a slightly different input, it can generate a different type of face. And now I think we feel like, okay, now we believe more that it starts to understand what drawing a face means, and it's actually pretty good at it because it's able to do a lot of different faces. And it's also becoming more useful to us. And also what's important is that we want to have randomness in a way that's very easy for us to sample from a computer. Right? So we can create this randomness very cheaply from a computer, feed it in, and then run the model. Right? So we don't have to create a randomness, but it's created by the computer itself. And computers are very good at creating these pseudo-random input that we can use. Okay, so let's say we want to give this random input to the model, and we want to generate some face. How can we go about doing this? Well, we could try to just draw the face in a single go, right? Just from having the randoms and removing all randomness completely at one single go for the model. It's one try. Or we can say you can remove some randomness iteratively. And this is going to be very, very useful because it's going to be somehow easier for the model to do, right? It doesn't have to do everything in a single step. It can remove some randomness and then basically feed it, run itself on its own output and try to remove some more randomness. And I think, as well as human beings, we probably, when we learn to draw, we draw things. We don't just draw everything in a single go. We kind of sketch it out and kind of iteratively improve on our drawing. And we're going to try to allow for the same abilities for this neural network. And okay, so why is this useful as well? Well, it's useful because now also when you think about different levels of randomness, and you can remove only part of it, right? Then also we have some kind of different levels of difficulties. So maybe if you want to go from a complete random input, some noise, to just removing some noise and putting some features there, that's kind of, maybe that's harder, right? Because it requires more of imagination to get going. But at the very end here, when we just have to finish the cheek, maybe that's easier. So suddenly as well, we're going to have different kind of levels of randomness in the input, and we have different levels of difficulties. So this is both useful for the model when it's being used, because it can iteratively try to improve on its improve on itself, right? It doesn't have to generate everything in one single go. It can generate a little bit and then kind of add to that. It runs itself on its own output, all right? But also if it sees different levels of randomness during training, so it has to go from left to right at these different levels, it's also good because it can start making some progress at a certain level of difficulty, and then it can start improving, and it can start learn something there, and then when it's learned something there and reach the next level, it can make more use of the more difficult examples. So I know you guys remember, but when we talked about generative adversarial networks, it was very difficult because then you have a kind of a critic and a artist, and they have to be very synced. So the critic needs to be able to give feedback on the level at which the artist is right now, right? Its skill level. But if one gets ahead of the other one, it breaks down. That's actually what happens during training. But here somehow we give different levels of difficulties during training, if we can create these examples. So the model is able to make use of some examples and start improving, and then we can make use of all examples. Okay. So in order to be able to create samples of different outputs, right? We need to be able to sample noise, and computers are good at creating certain type of noise, so we're going to use that. Creating everything in one single go is very difficult, so we're going to allow the computer to iteratively improve on itself. So it's going to be able to start from some noise, add some part of an image, but not remove all noise in a single go, and then keep going iteratively. And if you want to do that, right, somehow the noise needs to be part of both the input and the output. So if it doesn't have to remove all the noise, it can still be part of the output that it generates, and it can run itself on its own output. Okay, and handling different noise levels are good both for training, because it gets training example at different difficulty levels, and it's also good when we actually use it because it can iteratively improve on itself. Again, in GANs, the artist only have a single attempt to create a image, and then the critic criticizes it. And here, the artist and the critic has to be on a similar level, because the artist is supposed to fool the critic to feel like this is a good creation of a face, for example, right? So it's the artist creates a image of a face. The critic gets a real face from a distribution of images, and then it also looks at this fake face that the artist created, and it learns to critique and say, it's supposed to learn to say like, well, which one is the real image, which one is the fake? And the artist is supposed to fool the critic. So the critic feels or believes that the artist is actually creating real-looking faces. But it's very, very difficult because the feedback needs, like the artist and the critic needs to be on a similar skill level for them to kind of co-develop and co-learn together. Okay. So if we actually look at these, what drawing professionals do when they draw something, is that they start with some outline and then they add details. So it seems to be a good idea also from how human beings do this professionally. And that's what we're going to try to imitate. And also, as you can see here, they don't go from having some random noise and then removing it bottom to bottom, like top to bottom. They start from some outline and they add more details, right? Not just removing the top of the face, middle of the face, the low face. They go from some kind of outline to details. And it's also what we want to do. And I think this is why this is also very, very powerful, is because when you want to learn something, it's much easier to point in the right direction and make some progress than find the exact location immediately. So, right, if somebody asks you where Uzbekistan is, right, it's probably, you wouldn't know the exact coordinates or location, but you can point in the right direction. So maybe you point, if you're in America, you point towards Europe and you make some progress, and then you can keep going, kind of. But it's easy to learn that way and making some progress that way, when you have to get kind of directional feedback. Okay, so how we're gonna try to recreate this is that we're gonna have this type of setting, where we start with some noisy image, like a complete noise, Gaussian noise that the computer can generate, and then the model will start adding some features, right? Adding some beginnings of an image. So basically remove some noise and start going towards some type of image, in this case a face. And then when it's done this one step, it can run itself on its output and keep going. And then it can make even more improvements and even more decisions around how this face will look like, right? So it starts somehow from pure noise and adding some outlines of the face, and then it adds more and more detail at subsequent steps. And then we can run this until we're pretty happy with output and deliver it. And this is called, again, one single step of this is called denoising. So you remove noise and add details of an image. And if you do the denoising several steps, it's called diffusion. So that's where stable diffusion comes in. It does multiple steps of denoising. Okay, and we also, of course, want to add some abilities to go from text to images. So we have these correspondences, images with text descriptions. We also feed this and condition the model on this. So in its creation process, it can guide its generations by having access to this text. So it can kind of collapse into a space that's useful based on this prompt. And we don't need to start to understand language from scratch. We can leverage a pre-trained language model to get some good starting point of understanding language, right? That's helpful. But still, we need these corresponders to actually train the model. Okay, so that's like a very, very high level of how the diffusion stable diffusion model works. And we're going to go a little bit more detail and talk about how you actually create the training data around this, how you train the model, and then how it's being used. And then we'll end the lecture talking about some more nitty-gritty details. So, of course, it would be very, very nice if we had tons of these different outlines. So we would take an image from the internet, give it to some human being, and the human being could create some type of outline to details examples. But that would be extremely, extremely expensive to give a billion images to millions of human beings to kind of try to create different levels of abstractions. And so we're going to try to recreate it by using only the computer. And we do this by taking an image from the internet, which is cheap, creating noise, which is cheap, and then we just add these two together basically. And then we're going to add different noise levels. So we get an image, which is the image that we actually want to recreate. We add some noise that we can generate, a computer can generate, and then we get the input on this left side, and then we have the target, which is just the image that we had from the beginning. So we want to learn to go from this noisy version of the image to the target. So this is very, very cheap to create because noise is very cheap to create, a computer can do it, and image is easy to download. That's why there needs to be no human being in this loop. And of course, we want to have different types of noise levels because we want to be able to go from any type of noise level to less noise. Because when we actually, when we train it, we want to go from any noise level to less noise because when we deploy it, it's going to be deployed, iteratively running on itself. So it might come across a lot of different types of noise levels when actually being deployed. So we're going to just have different types of noise level to create different types of pairs for tons of different images and for tons of different noise levels. And also we're going to throw in pure noise sometimes. So then basically it has no idea about the image whatsoever. It has to just hallucinate to make up an image from pure noise. That's also important because when we actually deploy this, we want to be able to start from pure noise, right? Because we want to be able to generate from thin air something. And of course, we want to make this even more useful and not to sample randomly. We're going to add text that corresponds to the image to be able to guide that generation. So we can give a prompt to Dall-E or Stable Diffusion, and it generates the image that we want to see. Okay. Right, and then when we train this model, we now have a input, which is a noisy, image plus some noise level and noise. The model gets this input, and it gets the prompt that we feed through a language model just to kind of make it more useful features or latent features of it. We feed this to the model, and then it's supposed to generate a guess of how it believes that the real image looks like, right? And make a step towards the real image that we know that we have. And then we can have some loss function looks at the difference between the guess and the actual target that we want to reach, and we can give some directional kind of feedback saying like, hey, you go in the right direction, but this is how you can improve on yourself. So that's how we're going to be able to train this. And then when it's trained again, we're going to feed when it's been trained on all these different types of images and noise levels, we're going to actually start the model off using pure noise and some text prompt, and then it tries to take steps towards a real image or like an actual image. And then we can run this as many times as we want, right? Step 1, step 2, step 3, we just rerun the model, and we get a better and better image, and we stop at some point and say, hey, we're happy now. But of course, it's very important here because now that it's being deployed, there's no need to download any images from online or anything because it can generate an image from pure noise, which we can just create by the computer can create by itself. Okay, so all right, so that's kind of the little bit more detailed, high-level perspective of how Stable Diffusion works and image generation works. We're now gonna jump in a little bit more into how Stable Diffusion makes very interesting choices of how to improve this pipeline. And they connect a lot of different concepts that we've been talking about throughout the class. So first thing that they mention or realize is that details in images are very repetitive. And maybe you don't want to spend too much effort in your training and in your model in just generating details. So if you look at this, if you zoom in on this face, like these are probably not that hard for an AI model to add. They're pretty repetitive, all these pores and details and stuff, you can just, it's not going to be very, very hard for the model. That's what they believe. So they shouldn't put too much work on creating the details. It's hard to create the outline or the important features of a face, and the detail is going to be less demanding. I mean, maybe it's an empirical observation, but that's what they believe. And also, because these diffusion models like work on the pixel space. So it takes some pixel image, right? So maybe it's 1024 times 1024, adds noise of the same dimension, and then that's a pretty big input of like, you know, 1,000,000 pixels. And then it removes some noise and creates the same resolution again, right, with less noise, and it keeps running on it over and over and refines itself. And that's expensive then, because resolution is quite expensive. So it's a kind of a, the resolution that you're using determines the cost of running this training and in deployment. So it would be very, very nice if we could magically reduce the resolution of this image and run diffusion on the smaller images instead, right? So if you're able to make the resolution 8 times smaller, I think, right? The actual number of pixels are, you know, much, much smaller, quadratic, right? Okay, so what they do to accomplish this is that they're gonna do this thing that we talked about, right? Game of compression and autoencoders. So they're gonna try to push an image, right, and compress it to a smaller space, and instead of using just a random vector, a small vector, they're actually going to try to create a smaller image and then be able to kind of upscale and downscale without losing any significant information. So they're going to learn to compress to a lower resolution image that basically is a very good compression and summary of the image without all the details that might not be that difficult to recreate, right? So it's actually, when you look at this when it's being trained, the smaller image is actually like a smaller image, you know? So it just learns to compress this in a smart way, because this autoencoder that it creates is really good at creating these details. So it's very good at upscaling the image and increasing the resolution. And we're going to split this apart into the autoencoder into an encoder and a decoder. So the encoder is that one that takes a big image, compresses it to a smaller image, right? That's the encoder. And then also we're going to have a decoder that goes from a small image to a bigger image. And for now, we're just going to assume that we have these. They work really, really well at downscale and upscaling the image. And we're basically losing no information about the image in the process, because these details are not something that we really care about. Okay. So let's say now we have a perfect encoder and decoder. How can we utilize this? Well, we can now take our image from the internet, we can encode it to a smaller image, we can create noise in that smaller space, and then do the whole thing of diffusion denoising in this smaller space instead. And then when we're done, we can recreate the original image. Okay, so let's talk about this actually works in detail, but now, in de facto we can just redo everything that we did before, but we can just do it in a smaller space, which saves a lot of compute in terms of training, and also is much faster when it's being deployed. Okay, so how does this work? Well, we take an image from online that's big, we run it through our perfect encoder, we get a smaller image, right? So that's our new target now. We add this smaller noise as well, in resolutions. We get an input, and we now feed this input to our model with this prompt, and we try to remove some of this noise, right? We try to remove some noise, and then we can compare ourselves to our target and give feedback and improve on ourselves, right? So we just do this training now, but in this smaller space. And of course, it's easy for us to generate noise, different types of noise at different levels in this smaller space. And so we're just redoing this whole thing, and this turns out to work really, really well, right? So all we do is that instead of taking an image from online, we take an image from online, we run it through our encoder to make it smaller, and then we do the training there instead. And when we use this, right, so now notice we only use the encoder during training, but now when we want to deploy this, we're going to have some user typing on his computer a prompt. When we receive a prompt, the computer creates pure noise, right? So the full noise level, maximum possible. We have some model that encodes language, feed it to our denoising model. It gets the pure noise and starts making a step towards a real image. And then we can keep running this on the output as many times, as many iterations that we want to. And when we're happy, and depending on how much compute we want to make available, right? How many steps, there's some threshold, like, okay, get a kind of diminishing return, but you run it for a number of iterations until it's good enough, and then you feed it to your decoder, and you upscale to a image of the resolution that the user is interested in, and you deliver that. And as long as the encoder and decoder works really, really well, you're not losing out anything. Okay, so hopefully this makes some sense, and it's a nice trick to be able to get lower resolution images that makes training faster and deployment faster. Because this step of denoising, if we do multiple iteration, maybe we do it 100 times, 1,000 times. So it's going to be the number of iterations is going to be the most expensive part of this training and deployment. That's why it's nice, because we only decode once during deployment and we only encode once during training. So it's not very expensive. Okay. So we now said that we had this perfect encoder and decoder in an autoencoder. And now we're going to talk about how we get them, right? So, and why, what kind of tricks we use to make them work well. Okay, so in an autoencoder setup, right, we want to take some image from the internet, any image in a data set. We want to run it through our encoder to a smaller image, a compressed version, and then we want to run it through the decoder and upscale it, and we want to get back original image, right? We want to be able to do this loop without losing any information. And actually, there's a lot of nuances here that are harder than you might at first think. So first off, you got to decide, like, how do you measure if you get the original image back? What's a good loss function or perspective on how close these images are? Because you want to have some loss functions that you want to minimize the similarity between these images after being run through this autoencoder. But how can you do that? So one of the first things you can try, what people did, is that you can just say, we're just going to compare pixel to pixel. We're just going to take the pixels values in the input image, the pixel values in the output image, do a negative or something, or do the negative and make sure that the difference is very small, right? So what's good about that? The good thing about that, if the autoencoder recreates the original image perfectly, then the loss is 0. So the optima is good, right? When you do a perfect job, the loss is perfectly optimized. But of course, there's clear kind of drawbacks in how it's actually able to measure similarity in a way that we think is sensible. So let's say you take an image now and you just basically shift the image a little bit, right? These are still very, very similar images, but because they shift a little bit, the pixel correspondences, when you do the negative between two images, they're going to be very, very different. Like here, for example, these images are kind of shifted a little bit, so you're comparing an eyebrow with an eye, and you're going to see these images are very, very different, though they're clearly quite similar. So just doing the negative or the minus, subtracting the two images and looking at that is not sophisticated enough to capture a similarity that we as human beings perceive. Okay, so what can we do? Well, the first thing that Stable Diffusion decides to do is that they actually introduce GANs. And they say, well, GANs have been used for quite a long time. Empirically, we've seen that they're good at capturing details. So they're going to leverage this in this work. And since GANs are good at the detail level rather than the big picture comparisons, they're going to take small patches of each image, and then they're going to feed this patch, right? So I have a patch now from the original image and the recreation. You're going to feed these two patches to a critic, right? And this critic is trained, to say which one is from the original image, right? The true actual patch from a real image, and which one is from the recreation, right? So it makes a guess, and then we train it by saying, okay, this is actually, this one is the original, this one is the fake, so next time you see something similar, you do better, right? But then, of course, the encoder and decoder is trained to fool the critic. So the encoder and decoder is trained to make the patches look very similar from the critic's perspective. And this turns out just to work really, really well at capturing all of these different details. So, when you generate an image of a face, like you won't go and zoom in on the pores too much and care too much. As long as it looks quite similar, you're going to be happy with it. And that's what they leverage here as well. And of course, they do this on all the different patches and feed to this GAN. Okay, so this gets now solving kind of generating the details of an image. So we can downscale and upscale again without losing those abilities, right? Because we want to, when we ask Dall-E or Stable Diffusion to generate images for us, we want it to look realistic. We want the details to be there. We don't want to have a face with no pores or something like that, right? We want it to look realistic. And now we're able to do that, but there's like one thing that's missing in the setup is that we just have this local loss, but we still also want the overall image to look nicely, similar from a bigger perspective as well, right? We want the face to be put together like a face, not just the patches, being skin, but they want the eyes to be in the right place, etc. So we're going to try to also include a loss now, or compare these images from a more global perspective, not just patch level, but more global. And we're gonna try, because this is gonna be used by human beings. They're gonna judge the quality of this output. We're gonna try to imitate how human beings judge images, or how they think images are similar or not. So we're gonna try to compare these images in a way that humans would. Yes.
So if patch to patch doesn't match, can you have the model look at various groups of patches and versus another group of patches to see if they're similar? Or like how do you address that problem?
Oh yeah, so I think in this work they compare pairs of patches and they take the same patch on both places. And is that a problem now? Like, okay, is it a problem now that these patches aren't perfectly aligned? Well, if you think about it, because we're not using we don't subtract now and get a value. This model literally looks at both of these and says which one could be from an actual real image, right? Like which one is from the original image and which one is from the fake one. And if you look at this yourself, like this would be hard for you to tell because they look like they both come from real images from a face. So then, like, them being off in terms of not being the same patch is now kind of fairly irrelevant because you as a critic will just judge looking at that patch and saying, does this actually look like it comes from a real image or not? Which makes this loss now so much more informative because it's not as simple as just like doing the negative. It actually has to understand more how patches look like.
Right. So the critic is actually the model or the community?
The critic is another model. Yeah, so it's another model that's trained adversarially, right? So after we've done with everything, the critic is not used. So that's just, we're gonna throw away the critic when we're done. Okay, good question. All right. Okay, so we have the comparing the patch level done, so we are able to handle details, but we want to be able to handle the complete image, right? So we want to have some more global loss to compare the images, and we want to have something that, such these images look similar from a human perspective, because human beings are going to use this eventually. Okay, so what they do actually is they say that there's been a lot of work. So we talked about contrastive learning in this class before. So this is, again, self-supervised learning on how you learn good image features for images. All right, so what we do? Well, in this case, we take images from online. We say that concepts that appear in the same image are more related and similar in meaning than concepts that appear in different images, on average, right? When you look at a lot of images. So in contrastive learning, you just take an image, you create two random crops, so patches, and then you train a model to say like, well, if you feed a one crop to the model is supposed to be able to say which of all possible crops in my data set is from the same image and which ones are from other images. So it needs to be able to identify what patches or crops come from the same images, right? So here somehow, it would have to understand that if it sees a image or a crop or a patch of a human being with a leash, it's probably walking a dog, right? So somehow understand these two things are related, and it's more likely to be a dog that is walking than a cat, for example, right? Another crop. So it has to understand these different things, how they relate. And when you train this, it creates an output that you use, like a feature, a latent space feature, that summarizes the image. So basically, in its process, it creates a compressed vector that summarizes like a feature representation of this image, if you will. And it turns out that there's been a lot of work done where you look at the features and the representation that these models learn, and you look at the distance. So you take two images, you run it through this embedder that we got from Contrastive Learning, and then you get representation vectors, features, and then you look at a simple negative subtraction distance in this embedding space, latent space. That distance corresponds very closely to how human beings judge similarity or dissimilarity in images. So they basically take, how they test is that they take one image and then they might have, well, let's say maybe I don't know how to do exactly, but maybe they take like 5 images and then let human beings group them together of like, okay, which ones are closest? Or they take like one image and then 4 targets and say like, rank these images in terms of how close they are to this image. And then these models will do very similarly to how human beings rank these. So this is kind of empirical, which also suggests that actually we are also learning in similar ways. Okay, but why is this nice? Well, it's nice now because we have this embedder that we don't need to train it now, it's trained, so we can freeze it, but we have an embedder that can create global features of our images, and then we can look at the distance in this latent space, because the distance here, when the distance is small in this representation or latent space, then they're very similar according to a human being. So now we can optimize and minimize this distance in this latent space to get at the global similarity somehow between these images. Okay, so now we just combine these. So we have both a critic that we try to fool, and we have this embedder that we try to make happy by aligning the representation in this latent space. So we get both details locally and then globally kind of aligned. And this turns out to work well and converges nicely. You could imagine, for example, that these two losses would be contradictory and work against each other, but empirically this works well and they converge nicely. Okay, so to summarize, so denoising, right, when we take some noise and we try to refine it by adding details and taking steps towards images, can actually create from thin air or pure noise if you train it on different levels of noise. Diffusion is when we're able to do this iteratively, right? So we have a denoising model that's able to take some noisy version of an image and taking steps in the right direction to make it look more like a real image. When we do this iteratively, right, improve an image in several steps, it's called diffusion. If we condition on some language input, so we have language and image correspondences, we can make this generation not just random, but actually make you happy based on the prompt. So it adheres to the prompt that you gave it. It's a correspondence between the prompt and the actual generated image. So diffusion works on the pixel level, so it's expensive. So if you have a high resolution, you will have a very expensive model to train and to deploy. So if you can do it in a compressed, small resolution space, you gain a lot. So that's why Stable Diffusion uses an autoencoder to compress the image to a smaller image and does all the training there. And when we create these autoencoders, so encoder and decoder, we have to be careful about how we think about similarity to get something that is actually useful. And also we have to take somehow inspiration from how human beings judge similarity, because at the end of the day, our models are deployed to human beings, and we want to make them happy with our product. And I think also it's pretty cool because, right, in this all these different approaches, we used a language model that's trained on let's say, just next token or next word prediction. So that's self-supervised learning. We used denoising diffusion that we talked about before. We used autoencoders that were trained using GANs, so generative adversarial networks. And then we also even used a contrastive learning from images to get a useful representation that we can use for training our autoencoder as well. So it's like really cool how all these different self-supervised learning concepts came together to create Stable Diffusion, and how they're able to kind of stitch them together. And this is possible, of course, because they all rely on no labeled data, right? So they can be trained at scale. Yeah, so I think that's also like a very cool thing of how you can combine all these different things. Okay, and as well a little bit, I mean, I think also it's pretty nice that we can use a little bit of our human intuition to engineer and use AI. That maybe we can say, like, how do we think about when we draw images? It's useful to be able to improve on yourself, and also when we look, for example, at how do human beings judge similarity, it kind of corresponds to how these self-supervised learning, contrastive learning models judge similarity. It's also very encouraging that we're somehow also getting a little bit closer perhaps to understanding how we work ourselves and our brains learn, because we're starting to see these similarities. And again, also I think it's quite interesting is that, like, that creativity from neural networks comes from noise a lot. So, like, if you give the same input, expect the same output. And maybe as well, like, I think maybe a lot of us, we have the same routines, and if you want to be creative in your work, in your research, you might have to get out of your comfort zones once in a while and put yourself in weird positions. Maybe even if you just go to like a new setting and work, you'll be more creative because your brain is not good at making up randomness. It's good at leveraging randomness in your environment, which is also pretty cool. Okay, we also talked about the tip of the iceberg, and we made it a little bit more, we kind of filled in some bottom part here. That, of course, at the top we have ChatGPT and Stable Diffusion and this cool stuff that people are talking about. But this, of course, comes from self-supervised learning, foundation models, generative AI, that's been around for some time, and the researchers have been excited about, right? But then also, of course, the data. The data took a long time to create. The internet, we were not able to reproduce easily. So the data is so key to making these AI models work. And also something that I think a lot of people that work with AI underestimate. In research, a lot of times our data sets are curated, cleaned up, and structured for us in a way that the real world isn't. So the data is really, really important if you want to go from theory to practice. Okay, so that's for today. Yeah, if you have questions, I can take them now. Yes?
So for the encoder that they train, is that going to be a variational auto-encoder, or would that be like a normal auto-encoder?
Oh, that's a good question. All right. I mean, we didn't even cover variational autoencoders in this class, right? I don't know which one they used. I don't they used a variational autoencoder. I think they used a regular encoder. But yeah, it's a little bit, we can go talk about it offline.
What was the loss function that they used for the diffusion model? Right? Because I know they used the GAN and the contrastive learning for the encoder.
Yeah, the diffusion loss is it's called score matching. Yeah, that's I mean, it's not super mathematically involved, but it's a little bit mathematically involved how to define it. So I think the high-level intuition is that you're trying to go from like a distribution that's random Gaussian noise, which the computer loves to create. That's like one distribution. It's Gaussian noise, and then you have a distribution of images. All right. You want to be able to sample from your Gaussian noise and then project yourself or transport yourself to this space of images. Okay. And yes, it's very hard if you just take random noise and you should take one giant step to the space of real images. Okay, so let's say the images live over here and the noise lives over here. It's very hard to just be like, bam, jump. But if you're smart about it, you can create training samples. So during training, you don't have to go all the way like this. You can create samples all the way in between. So I mean, you can take an image, add some noise, and end up in the middle between the full Gaussian noise and the complete images. So then during training, you can start to learn, and a loss is basically directional, mean that, like if you're here and you get a training sample, you take a small step towards the real images, you get like a directional feedback saying like, okay, are you taking a step in the right direction? That's the kind of feedback you get, which is very nice. It turns out that's nice feedback to get. That's easy to learn from. And then it's nice because now during training, you have seen all the different combinations of like being in between the full Gaussian noise and the real images, and you've seen everything in between, right, during training. So now that when you're being deployed and you only fed this thing, you can actually take steps like this along this from noise to images space and actually end up at a realistic image. So you can find your way by removing noise iteratively, like diffusion, and find yourself in the space where you want to, as long as you take steps in the right direction. So basically, right, now since this model has been trained to get from America to any place in Europe, we can say, and it learned by taking the right steps. So then we can say, hey, let's go to Uzbekistan. It can be like, well, I'm going to start taking a step towards Europe, then a step towards there, step, and then eventually will find itself in the right place, basically. Does that make sense?
Yeah, so like it judges the direction, not like necessarily whether it was able to go and what. It just judges whether it was getting close there.
Yeah. Yeah. All right. Thank you, guys.